You get it?
So I missed that.
It's bouncing? You hit record? It's what? Okay, cool. I will begin. Heavenly Father, we thank you for this day, and I thank you for all these students who made it here today. Just pray you help us, just bless our time together, help us to glorify you again, Lord, we do. In your name I pray, Lord Jesus. Amen. All right, so we went over a few very powerful toys last time, right? And I think after today is done, if you kind of go back and you look at some of the questions we asked early on in here, they'll all be kind of trivial. Like, you'll start going, oh, well, I know what this is because of this theorem we covered today. Like, a lot of the hypotheticals that we asked are just answered completely by a lot of the theorems that we're covering today and last time. But anyways, this is lecture 17, so let me get to it. So I'm going to get around to a few things that could have gotten to a lot earlier, some of them, and but I have no regrets. No regrets about this lecture. I'm pretty happy with where it ended up in the story here. Little number theory and finite abelian groups. Well, oops. You have to. I just say little number theories, really. Yeah, I moved the finite abelian groups to last time. I got to change the title of this thing. We have been using, without proof, a few things in here, right? One of them is that the Euler phi function of a prime is p minus 1, right? We also have been using, without proof, that the Euler phi function of p to the power k is p to the k minus p to the k minus 1. And we've also been using, without proof, that the Euler phi function of relatively prime s and t is the Euler phi function of s times the Euler phi function of t. One of the things I would mention to start with here is that I'm not using phi as an isomorphism here, right? I'm using phi as the Euler phi function. If I talk about an isomorphism in this lecture, I should be careful not to use the symbol phi, as it has a reserved and special meaning. All right? In fact, and perhaps that's a good reason to never use phi as an isomorphism in this course, but we don't operate like that in here, right? So, proposition. First proposition is that if p is prime, then the order of the group of units of Zp is equal to p minus 1. And that's equal to the Euler phi function of p, right? Now, let me just say once and for all that we defined that the order of the group of units, right, is nothing more than the Euler phi function of n. I mean, that's essentially a definition of the Euler phi function. What is the Euler phi function? It's the number of integers relatively prime to n, right? Up to n. So, and what's the group of units? It's the collection of all integers that are relatively prime to n, right? Modulo n. So these are the same thing, right? We proved in a previous lecture that the group of units actually is a group of units. So there's also that. I should mention, by the way, guys, if you look at other things, un is sometimes denoted like this. Other people will call un this. They'll call it z mod nz, with or without the parentheses and a little x up here. Right. This is the same kind of notation as like c with an upper x. It's the non-zero complex numbers. They form a multiplicative group. That's the multiplicative group inside Zn. Or you'll also see this. Anyway, I'm sticking with Galilean for the most part. So I'll stick with un, but just a comment. Okay, so how do you prove this? The proof is like really stupid. It's just counting, right? What's up? 1, 2, 3, p minus 1, right? All of these numbers are what? Relatively prime to p. How do you know that? P is prime. It's kind of the definition. The only divisors of p are itself and 1, right? In the positive integers. And so you can count, right? The number of things in there is p minus 1, and that's it. The next proposition isn't much different. If p is prime, then the order of u of p to the power k is equal to p to the k minus p to the k minus 1. All right, and of course that's equal to the Euler phi function of p to the k as well. What's the proof? Well, the divisors of p to the power k are what? We can list them. 1, p, 2p, right? 3p. We're going to be here a while. No, let's skip ahead a bit. P times p. When you have p of them, that's p squared, right? And then you've got p plus 1 times p. I don't know how many of these you want me to list, but we keep going and going and going until eventually we get to what? P to the k minus 1 times p, right? The next multiple past that is p to the k, which of course is 0, mod p to the k. And so that's a complete list of multiples of p. It's not possible to have divisors other than that of a prime to a power k. Yep.
I could be forgetting something, but isn't there a problem with saying 2p and 3p? So those don't aren't guaranteed to be divisors of p to the k. So it's like, think of it like 7 to the k. You get like 49. Like 7
Yeah, you're right. You're right. I'm listening to these wrong.
2's and 3's not divided.
Yeah, you're right. You're right. I should just do what? I should do. I'm sorry, I'm an idiot. P squared, right? Yeah. I don't know what's wrong with me. Let's see here. There. Thank you.
And should that only go up to p to the k minus 2 times p? Because p to the k plus 1 times p is p to the k.
P to the k. Yeah, you're right. Another good point. Thank you. All right, have we gotten it all out? have we fixed it? My notes need some work. All right. Oh well, eventually I'll learn what divisors of p to the k are. So someday. Anyway, you can count 1, 2, 3, 4, k minus 1. Excuse me. How many? K minus 1. See, that's not right.
One is like p to the 0.
Let me instead write this as p to the k minus 1. And then I think the counting is, well, you guys have confused me. Let's see here. 5 squared, right? It's 25. So this is, this has what? 1, 5, 10, and you guys are, you talked me out of something I shouldn't have got talked out of. It's 2p, it's 3p, and so forth and so on. You guys, what you do to me? What have you done to me? Yes, but think about it some more. What are we doing? We're not just looking for multiples. We're also looking for what? I'm not saying 10 divides. It doesn't matter if 10 divides 25 or not. 10 has no inverse mod 25 because 10 times 5 is 0, which means it has no multiplicative inverse. The condition for a number to be in UN is that it's relatively prime to n. It doesn't have to be strictly a divisor of n, right? It could just be, it could share a divisor. Like, so the point is the greatest common divisor, right, of 2p and p to the power k is what? It's p, which is not 1, right? So therefore, 2 to the p, 2p is not an element of u to the p power k. That's, I overstated it. We're not just looking for multiples of p. We're looking for anything that's not relatively prime to p to the power k. So any multiple of p will have a greatest common divisor of p, or p squared, or p cubed, or whatever you happen to have inside there, depending on the multiple. And of those, and then when you count these, how many are there? Well, that's why I had the p squared here. It's easier to see the counting, you know? So there's like p of them, and there's another p, and then there's another p, and so forth and so on. How many are there? There's p to the k minus 1 of these. And so if you take the total number in z to the pk, minus that gives you the number of integers which are relatively prime to p to the power k. Yeah.
Should we not include 1 in the list then?
Oh, yeah. I'm sorry. Very good, yeah. Sorry. Yeah, you should be confused by that. 1 should not be there. Man. Oh, well, anyway, now I've wasted entirely too much time on this trivial counting argument. And it really is trivial. All right, so so there we go. That's why we have the p minus 1 formula and the p to the k minus p to the k minus p. If you don't believe the counting here, look at like 7 cubed and just work through it. You'll see it, what's happening. Even 5 squared. Just thinking about the counting in a specific, for a specific p will convince you that our counting of the things which are not relatively prime to p is correct here. Sorry, what I should have done is done a specific numerical example. Then you would have all believed me. So, oh well, too late. All right, theorem. If s and, so suppose the greatest common divisors of s and t are 1, then u of the group of units of order st, well, not order st, but of st, mod st, I should say, is isomorphic to us direct product with ut. Right? And so, of course, immediate corollary to this, right? What's the corollary? The Euler phi function of st for relatively prime in s and t is equal to Euler phi function of s times the Euler phi function of t, right? So we'd like to prove this theorem. All right, so this is actually group theory, not just counting I can't do. Let's do it. Is there a question or something I've written, something I've said, something left unsaid? No? Oh. Which part? I mean, this is your course. You can ask questions. I mean.
I feel like if I once you go through the proof, I'll understand better.
Oh, okay. So we're trying to show that this, which is so here, this is the group of units. So like we have n equals to st here. All right. So anyway, here's the we're going to propose an isomorphism psi from ust to us cross ut. How are we going to do it? The way it's going to work is we're going to say psi of the equivalence class x, and this is mod st, all right, is going to be equal to the tuple, the 2-tuple, the equivalence class of x mod s, comma, the equivalence class of x mod t. So I'm being explicit. You know, we can always write z mod n as, you know, like this, right? And so when we do that, that's still a little bit ambiguous. When we've got multiple moduli floating around, it helps to put a little sub n here, you know? And so that's what I'm doing, because we're going to work with equivalence classes mod st, equivalence classes mod s, and equivalence classes mod t all at once. And so it's important to explicitly denote that in order to make sense of the proof, right? That's my proposed isomorphism. So what do we need to do to show that that's actually an isomorphism? We got a lot of work to do. First of all, we need to show it's a function, right? It's not even clear at the start that it's into, all right? So what does it mean to be into? Is it single valued? Is it, is it into? Is it single valued? These are things we have to figure out, right? I guess I'll start with single valued. What should we do there? Suppose that you have x st equals to, say, x prime st. What would that mean? What's the relation between x and x prime then? Some multiple of st, right? So times, let's say, jst. That's what it means, right? For these equivalence classes to be the same, it means that they differ by some multiple of the moduli, in this case st. And so if we look at psi of x prime st, what's that look like? Well, that's the tuple x prime sub s, x prime sub t. All right, but what is that? X prime is x plus, I'm going to emphasize that this is s times jt sub s, and over here we have x plus t times js, emphasis on the js times t there, sub t. But by the rules of modular arithmetic, mod s and mod t, those multiples get squashed to nothing in the equivalence class construction, and we're just left with xx. Which shows what? So therefore, psi is single valued, is a function, right? It remains to show, though, that my codomain is actually legit. So we should do that. What does it take for the image to be into? So I'm working on into now. What do I mean when I say into? In other words, if x st is an element of u st, is it in fact the case that x sub s is an element of us and x sub t is an element of ut? If that's not the case, then we're in trouble, right? All right, so what does it mean? So let's look at it. What does this mean? This means that the greatest common divisor of x and st is equal to 1, right? But going back to Bazoo, what do we know? So there exists what? There exists, say, whatever letters you want here. Let's say A and B, such that what? Right? So what's that show? That shows that A times x is equal to 1 minus bst, right? So what's that say? That says that A is equal to x, to use my bracket notation, that means A is equal to the, excuse me. Oh, goodness gracious. Sorry, I'm an idiot. So there you go. That's it, right? That shows that what? From this I can see that x sub s inverse is equal to A, right? And x sub t inverse is equal to A sub t, right? Because this shows that ax is congruent to 1 mod s or mod t. which is to say that the equivalence class of A is the inverse of the equivalence class of X, right? Which shows that X is in U sub S or X is in U sub T. So the map's into. Let's see here. Then what should we do? We should check the homomorphism property, right? Is it a homomorphism? It's a function, right? Great, but we were looking for an isomorphism, so we need to show that it's first a homomorphism. So how's that go? Well, psi of x st times y st is what? By definition of multiplication, multiply the representatives, right? Then by the definition of the function, that's xy s, xy t, right? But then by the definition of multiplication mod s or mod t, that does this, right? Right? By basic modular arithmetic. And then by the definition of the direct product, we can rewrite that as the tuple xs xt times the tuple ys yt. So here is definition of us cross ut as a direct product group, right? We multiply component wise. And what's that? Well, that's exactly the that's the function of x st, and that's times the function of y st, right? Thus, psi is homomorphism. What remains? What do we still need to show? Yeah, bijective. All right, so, but we can do some counting here perhaps. Oh, well, I guess I can't. Well, huh. Oh, yeah. All right, well, okay, bijective. All right, so, let's see here. What do I do next? Yeah, I don't agree with my notes here. I don't know. I said that since UST and US cross UT are finite, we show it's a bijection if we show injectivity or surjectivity. I don't think that's quite true, though, because I need also to know that the groups have the same size in order to make that jump. Same cardinality, right? So I suppose we should show surjectivity. So what do we need to do surjectivity? So let's let x sub s, and I suppose I should do y sub t, right? Maybe I should, let me do y and z here. So that's going to be an element of us cross ut, and we're looking to find what we want. We wish to solve what? We wish to solve psi of x st, right, equals to y sub s and z sub t. Which means what? We're trying to find, but this is equal to what? This is by definition x sub s, right? X sub t. So what are we trying to do? We're trying to solve two things at once, aren't we? We're trying to simultaneously solve x sub s equal to y sub s, and x sub t equal to z sub t, right? Or if you like, x is congruent to y mod t, and this is saying x is congruent to z mod, oh, I'm sorry. These are both s's, right? So the first one's mod s, and the second one's mod t. Why can I solve this? This is a system of congruences of relatively prime moduli. Hence, x is unique mod st by Chinese remainder theorem. Chinese remainder theorem says not only does this system of congruences have a solution, it has a unique solution, mod st. So that shows it's onto. And I think we accidentally showed it's one-to-one. Because there's only one x which maps to yz by the uniqueness of the solution in the Chinese remainder solution. Consequently, it's a bijection. Consequently, that's an isomorphism. Right? You're like, Chinese what? Right? How many people here have seen the Chinese remainder theorem before? How many have not? Right. It's not technically part of the prerequisite chain, but if you've had number theory, then you should have seen the Chinese remainder theorem. Now, I have pity on you, so I'm going to prove it for you now. And the rest of you, you'll have to bear with me. Or anyway, you're probably rusty, so it wouldn't hurt you to see it again anyway, right? Yeah. And the Chinese remainder theorem, it's worth proving because not only is the proof interesting, the proof actually shows you how to calculate, how to actually solve a system of congruences. So I have an explicit example here. But anyway, because I can't count, I'm a little bit behind, so I must project. So eventually I'll learn how to count someday. Oh, look. A homework problem. A new homework problem. Hooray. It's not posted yet, but anyway. You're like, my life is complete. Now this lecture has a full set of homework problems. Woohoo. Am I right? Maybe not. All right, so I'm greedy. Rather than proving the Chinese remainder theorem for two things, I'll prove it for a bunch of things because the proof is just as hard. So why not just do it right the first time? So suppose I want to solve, first of all, let me make this a civilized size. Are you charging? You better be charging. All right, fine. So let's say, suppose we have these relatively prime moduli, M1 through MR, all right? And we're trying to solve the system of congruences, x equal to congruent to A1, x congruent to A2, x congruent to AR, each with respect to the respective moduli. The theorem says there's a unique solution modulo M. In other words, there's a single x I can put here, 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 and here, such that it solves all of these at once, and that's unique up to this modulus, all right? So here's the way you do it. You define these M, big M sub k's by the product of all of the moduli, like the total modulus, let's call it big M, divided by the kth modulus. So this is a very interesting number because it has all of the moduli in it except for the one. So like this is 0 mod M sub j as long as j is not equal to k. That's the significance of this thing. It's 0 except when you're at M sub k. Right? Only in M sub k is it non-zero possibly. So of course the greatest common divisor of this and that is 1 by construction, because big M sub k has gotten rid of the one thing that could be could be divisor larger than 1. See how that is? Right? If, like, for example, if well, here, this one. If I have, it's helpful to have like a specific number. So if M sub 1 is 2, M sub 2 is 7, and M sub 3 is 11, then big M would be 14 times 11, which is 100 and what? 51? Yeah. And then M sub 1 would be, M sub 1 is 77, M sub 2, what did I do? Is it 154? Oh, that makes sense. Thank you. So that's this divided by 2 gives 77. That's better. Thank you. I was about to get really confused. Thank you. M sub 2 is 22. M sub 3 is 14, right? So these guys are relatively prime to, so this is relatively prime to 2, this is relatively prime to 7, this is relatively prime to 11, for example. All right, so for each then, you have by Bezout's theorem, there exist y sub k and b sub k such that this linear combination is 1, right? In other words, y sub k times m sub k is congruent to 1 mod m sub k. In other words, this y sub k is a multiplicative inverse mod big M sub k. So by math magic, consider this. These a sub 1s are coming from up here. You'll see why this is a good idea in just a second. So a sub 1, a sub 2, a sub r, and the y's again are coming from Bezout's, finding the inverse of the m sub k, mod m sub k. Well, if you look at this, mod what? So if I look at this x mod m sub I, everything is 0 here except for the ith term. So the only thing that survives modulo I is this. A sub I, m sub I, y sub I, right? But remember, mod sub I, this m sub I, y sub I is congruent to 1. So this just goes to 1, and you're just left with x is congruent to a sub I, which is just what we wanted. But I is arbitrary, so you've solved all of the congruences. And it's better than just a proof, because it shows you a method that you can calculate the solution, right? Let me show you how it works. For example, if I'm going to solve x congruent to 2 mod 3 and x congruent to 7 mod 11, what I do is I calculate my total modulus of 33, and then it gives me the big M sub 1 of 11 and big sub M 2 of 3. When there's just 2, they like flip-flop. So it's kind of cool. So I have to figure out what is 11. What's the inverse of that mod 3? The inverse of 11 mod 3 is 2, right? Because 2 times 11 is what? 22, which is what? It's 1 mod 3, right? And the inverse of 3 mod 11 is 4, because 3 times 4 is 12. For larger problems, you're going to have to do the extended Euclidean algorithm to find the inverses here, right? So this is somewhat easy because it's a low number. We can actually guess the inverse. So then put it together. I used the proof, which said I should construct the solution like that. So here my a sub 1 is 2, my m sub 1 is 11, and my y1, the multiplicative inverse of m1, was what? 2. And then I've got 7 for a2. I've got my m sub 2 of, 3, and my inverse of m sub 2 mod 11 was, my inverse of 3. Yeah, it's correct as it's written. Sorry, words. Anyway, so you multiply those. That's 44. That's 84. But we're working mod 33, right? So you split off so you get 128, and mod 33, that's congruent to 29. Because 99 is 0 in this world, so 99 plus 29 is 128. And it's easy to go back and check that 29, right, is simultaneously a solution to both of these. Like 29 is equal to 2 mod 3, and 29 is equal to 7 mod 11. It's not an accident. It's an inescapable truth. We've proved it in general, okay? So anyway, that's the Chinese remainder theorem in its simplest form. There are worse versions for moduli which are not relatively prime. This is part of an ongoing, lengthy technical discussion that you can get into. I'm just showing you the most beautiful and simple version of it. Modulo the storytelling. I have not been given any sort of indication as to why it's Chinese. There's some story you can tell. So you can use the Google. Let's see here. Suppose M1 through M sub r have the greatest common. So in other words, you've got relatively prime moduli. Then guess what? The group of units of the product is isomorphic to the direct product of the groups of units of the factors, like that. And it's essentially, it's just the same proof we went through, except instead of being a 2-tuple, you do an r-tuple. You just take the total modulus and you string it out into the M1 modulus, M2 modulus, MR modulus. The proof that this is a homomorphism is like literally the same as what I've got covered up right now. And the fact that this mapping is surjective and injective is the Chinese remainder theorem. All right. For example, if you look at Dummett and Foote, he proves the Chinese remainder theorem, and then he states as a corollary that this isomorphism is true. So for him, the primary result is the Chinese remainder theorem, and this is just a corollary to the Chinese remainder theorem. So it kind of depends on your perspective. But so there you go. That's why group of unit. That's why the Euler phi function works as it did. And now, last time I showed you how we could, take an abelian group of order such and so forth, and there's different abelian, different isomorphism classes, right? For example, if we had something of order 16, ooh, that's too complicated. Let's do something easier. 18. So 18 is what? 2 times 3 squared, right? So the isomorphism classes are what? You got something like Z2 cross Z9, or you got Z2 cross what? Z3 cross Z3, I guess that's it. Right, if I made this 36, then there'd be more choices. But basically, you just look at the prime power factorization, and you can look at different possible cases, right? Excuse me. And so for any finite abelian group, we can find it in the isomorphism class of one of these guys. That was what we said at the end of last class. What I'm showing you now is that any group of units, we can also find out what it's isomorphic to in terms of like a direct product of fundamental groups of units, so to speak. So for example, there's a few basic facts that we need, and I'm not going to prove these. Some of them we've seen already, right? How many numbers relatively prime to 2? Just one of them, right? So that group of units is the trivial group. So in this world, we would say it's 0. U4, how many numbers relatively prime to 4? 1 and 3, right? So that's Z mod 2 up to isomorphism. This one happens to be that. Again, this is a sort of technical result that we might prove sometime. And then here, again, thank you, Mr. Gauss. I guess we should probably call him Dr. Professor to be doubly respectful, following Landon's example. But, Gauss is, I'm not Gauss. Anyway, so there's this result as well. So the group of units of p to the power n is isomorphic to z to the pn minus 1 for any odd prime power. So I need, I think the oddness is with p, not with n here, okay? So this is a wonderful result. I asked questions early on like, what do you think this group of units is isomorphic to, right? And up till today, that was just kind of like a mysterious, we've got to do a truckload of calculation to figure it out, right? now it's as simple as looking at numbers being relatively prime and applying the theorems we just proved. Like, for example, U200, well, that's 5 squared times, this is 25 times 8, right? And so these are relatively prime, right? 8 and 25 are relatively prime. I think we can agree. So this is isomorphic to the direct product of U25 and U8. But U25 is isomorphic to Z25 minus 5 by what's up here. And U8 is isomorphic to Z2 cross Z2. That we have seen explicitly. Remember, we've calculated U8, 1, 3, 5, 7, was it? And remember the Cayley table? It looked just like the Klein 4 group table. It had three elements of order 1. It was on the last test. Why aren't you guys complaining I haven't posted a solution to the last test? You're just like waiting to the final to study? You don't care? Dangerous game, my friends. Let's see here. I mean, I believe in recycling, but hopefully not for this course. Let's see here. That's not true. I don't really believe in recycling. Let's see here. But I do want students to just take this course once. It's true. Anyway, Z20. So there you go. The group of units of modulus 200, order 200, not order 200. It's this thing. What is the order of this group? 20 times 2 times 2, 40, 80. There's 80 numbers relatively prime to 200. We can all agree figuring out that there were 80 numbers relatively prime to 200 was much simpler the way I just went through it than if you started listing them, I think, yeah? 405 is 5 times 81, I think. And so that's this. Now, the group of units of any prime is just isomorphic to Z p minus 1. I think this we've known for a little bit. This, again, using this result here is 81 minus 27, which is, so Z4 cross Z54. Now, Z54 you could break down further, right, using this kind of stuff. The things we went over last time if you wanted to. U195, 5 times 3 times 13. So you got yourself a U4. What? Where's that 4 coming from? No. No, 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 no. Oh, no. 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 That should be Z4 and Z2. That would make sense here. This is total nonsense. Sorry. Anyway, what idiot wrote these notes? Let's see here. I want my money back. All right. There are fun questions you can ask here, like, how many automorphisms of Z100 have order K? In other words, how many isomorphisms from Z100 to itself, when composed with themselves k-fold times, give you back the identity mapping? That's a terrifying question without the theory we have here. The thing is, the automorphisms of Z100 are isomorphic to the group of units of 100. We proved that a number of lectures ago. You may have forgotten, but it's true. So U100, we own that now. That's an easy thing to figure out. U100 is U4 times U25. Good, at least I'm not making a mistake here. Now U4 is Z2, and U25 is Z20. So to analyze, so basically the question becomes, how many elements of order K are there in Z2 cross Z20? See, because isomorphism preserves the number and order of elements of each order, you know? So instead of analyzing Z100, which is kind of hard to think about, we can analyze Z2 cross Z20, walk in the park, right? So in particular, if I'm looking for group elements of order 4, I need to have A comma B either have order of A is 1 and order of B is 4, or order of A is 2 and order of B is 4. And so there are actually 2 elements of order 4 in Z20. So that means, and there's many ways. You get it. These are the 4 elements of order 4. So there are 4 automorphisms of order 4 in Z100. Tricky? Not really. I mean, once you understand it, it's simple. But if you're not aware of this theory, it's a very mean question. All right. So some unfinished business for Maz Little Theorem. If p is prime and a is not equal to 0, then a to the p minus 1 is equal to 1 mod p. The proof of this is not hard. So Zp has p elements, up has p minus 1 elements, right? If you look at the subgroup generated by a, it's a subgroup of up, right? So that means that the order of a has to divide the order of up, right? And the order of up is p minus 1, so a has to divide the order, a has to divide p minus 1, which means that there exists an n, which p minus 1 is a multiple of the order of a. But then, of course, a to the p minus 1 is a to the n times order of a, but that's 1. So this is for Maz Little Theorem via group theory. This is something you would have seen in number theory, yeah? Okay. Proved a rather different way, right? Yeah. This proof is simpler. Euler's theorem is trivial in our current context. If x is, I couldn't even find it in Galilean. I don't think it's even in there. But this is important in number theory, right? So if you have x in the group of units of modulus k, then x to the power Euler phi function of k is equal to 1 mod k. It's a tricky little business here. This is just, remember that we had a theorem that if you take any element of a group and you raise it to the order of the group, it's the identity? We proved that as a corollary to Lagrange's theorem. You just apply that here to u sub k because the order of u sub k is phi to the power k. So anything raised to the order of this group has to be the identity in the group. That's it. And that brings us to encryption. So what is encryption? Well, I mean, you guys use encryption all the time, right? Whether you know it or not. You know, you do anything secure banking or stuff like that, it's all encrypted. It's kind of behind the scenes. You don't see it, I don't think, but it's there. If it wasn't there, people could just like intercept your electronic communications and read your credit card number off of it and stuff like that, and that would be bad because there are bad people in the world, right? There are. Trust me. I've met some of them. Anyway, so this is the RSA encryption scheme. Listen, not screen. What's a trapdoor function? A trapdoor function is what it sounds like. What's the thing about a trapdoor? It's hidden. I guess that's one thing. You go in, but you don't go out, right? It's really easy to go through it one way, but it's really hard to go through it the other way, right? I mean, that's the thing about a trapdoor. So that's the idea of a trapdoor function, something that's really easy to do, but impossible to undo. Unless you happen to know, the secret thing that allows the trapdoor to swing the other way, let's say. So this method I'm about to describe is from the 70s. Apparently there's some British intelligence officer, Clifford Cox, who also invented this same thing. Anyway, here's how you do it. You choose a pair of large prime integers, p1 and p2. You define n as the product of them. All right? That's the first thing. Pick two large prime numbers. You calculate the product of the prime numbers, and you pick some encryption exponent, which is relatively prime to the Euler phi function of n. All right. This we all do out in the open, and then you publish this thing, this n, what's called the modulus ne, the encryption exponent. All right. You just tell the world n and e. Send me a message using n and e, using the RSA system. Your friend takes a message, he, she, it, whatever, transcribes it into some kind of standard alphabet code kind of thing. Whatever. There's various ways to do it. For example, I'm going to look at the message J, which in the alphabet code would be 10 in a second. Then your friend takes the n and e, which you've published publicly, and he raises the message, which you've encoded to be an integer, all right, to the power e, modulo n. This makes this, I mean, the n here could be huge, all right? It's a very bigly number. And, sorry, I have to get that out of my system. But anyway, so you exponentiate modulo n, your message, and then he sends it to you. He sends you this encrypted message, f of m, to you, without even hiding. He's just out in the open. Nobody can undo it, because this exponentiation, modulo n, is a trapdoor function. But the thing is, you, knowing how you made the n, know that the Euler phi function, you just take the 1 minus the primes and multiply them, and that gives you the Euler phi. And you can also calculate, you can find an inverse mod phi n of your encryption exponent. Nobody else can do this because they don't know n. They don't know the factors in n is the thing. You're like, well, can't they just factor n? The thing is, the primes you're taking have hundreds of digits. There's no way to nicely factor primes with hundreds of digits. It's like an impossible numerical problem in finite computer time. The impossibility of that is what keeps encryption from breaking. And but the thing is, right here, you take m to e to the d, but that's equal to m to the 1 plus k Euler phi function. But then Euler's theorem says this piece drops to 0, back to, that's just the identity, right? So you got m to the 1, which just gives you m. So raising to the power d undoes the encryption, just like that. And then I just have a toy example down here. I used my primes 13 and 17. This would not be very secure encryption. Very useless, really. And so I picked the message of j, which is 10. Encrypting it, I have to raise to the, I choose an encryption exponent of 37. The way you actually raise things to the 37 power is not directly. You do it in steps, right? Like 37 is the square, the square, the square, the square, the square, the square, the square plus 1. After one multiplication. So I repeatedly square and then eventually multiply by 1. You keep track of what you're doing. You can chop down a number of steps. Anyway, long story short, 23 is what you get. 10 to the power 37 modulo 221 is 23. And then I calculate the encryption, the decryption key as I describe here, and it works out to, anyway, so I find out that the, where was it? Well, anyway, if you read through here, you'll see that I find the d, when I raise it to the power d, it undoes it, and we get back to 10. When I did this in number theory with you guys, some of you who had me, one or two, I chose an encryption exponent of 49. And what happened was you guys raised the message to the encryption exponent, and it didn't scramble it. It just took 10 and sent it to 10 again. And it was very confusing for me. When I came back in the room, I was like, what? Because I left the room to let you guys scramble it. And I came back, and you were like, yeah, it's just the same thing again. I'm like, what? Anyway, so the reason for that is that if you raise this to the 48th power, that's an example of what's called a group exponent. It's automatically the identity. And so at the 49th power, it just goes back to what it starts again for anything. So the fact that I just chose, there are hidden dangers in this encryption. I'll just say that. Anyway, thanks guys. I'll shut up.